Well, welcome everyone. Thank you for joining us, and sorry to get started a little late. We know we have some people still jumping onto the webinar, but we hope you're all healthy and safe and prospering during some challenging times right now with the pandemic. It's great to have you join us today for a really exciting topic, stone as structure, or if you prefer my notion that stone is structure. So I'm Karl Doucas from Picco Engineering, and today I'll be joined by some really dynamic leaders in the field of natural stone and experts on our topic of the day. They are Michael Picco, President and Founder of Picco Engineering and Vice President of the NSI, Matthew Innocente, Structural Engineer at Picco, Steve Webb, Co-Founder and Director at Webb Yates Engineers in the UK, and Bryan Thorburn, Director of Business Development, Europe and the Middle East at Polycor. So you will learn a lot more about each of our presenters shortly, but for those of you less familiar with Picco Engineering, we are an award-winning structural engineering and professional services firm in Toronto, specializing in stone cladding, masonry, and engineered facade systems. Our creative solutions extend beyond facades to complex geometry, feature architectural installations, BIM delivery in both residential and traditional structures. So our plan for the next 60 minutes or so, first we'll review a cool private mausoleum project in Toronto with Matthew. Structural stone columns reinvented, something a little different as far as stone columns go at Belmont University. And Stairmaster. No, I won't talk to you about the obsolete exercise machine, but a dual reference to the owner of this house and Steve Webb, the man you will meet a little later, but someone we collaborated with for a very special project, which we will showcase here. And our past, our future, our present. The order of those terms is correct because the future is today. And we will talk about the potential of stone as structure, how we got here, and the opportunity right now. And we will do that with some brilliant minds and companies working with stone. So we hope you are all part of the conversation as well. Please provide your questions through the chat feature for our panel during our roundtable segment later on. So let's get this rolling. We hope you learned something new and that you question and challenge those thoughts you have about the perceived limitations of stone. And now to kick it off, I'll hand it over to Matthew.
Thank you, Karl. Good morning, everyone. My name is Matthew, and I'm a structural engineer here at Picco, specializing in cladding and natural stone engineering. The first case study that I'd like to present is a mausoleum located here in Toronto at the Mount Pleasant Cemetery. To start the case study off, I'd first like to define what we mean at Picco when we say stone as structure. Basically, it's whenever a stone element is used to carry or transfer load other than self-weight or the weight of other stone cladding. In the case of this mausoleum, the entire superstructure is composed of gray Chinese granite, bearing on a cast-in-place concrete foundation that's on helical piles. The mausoleum is about 30 feet wide by 21 feet deep and 18 feet high, with walls that are 12 inches thick and roof panels that vary from 5 inches to 7 inches, depending on the location. For this project, our client was originally interested in using solid stone walls, but had considered a more standard roof structure. We were able to work with the client and propose the idea of constructing the entire superstructure, both walls and roof, out of natural stone. The challenge, therefore, was to provide support for the roof such that it could span a clear 10-foot ceiling space. Our solution was to use a series of hidden internal columns that bear down directly on the ceiling panels. This worked well due to the inherent strength of this stone. A more significant exercise was involved with developing all of the notches and keys in the roof panels and other stone elements that prevented sliding and transferred lateral forces down to the foundations. Our design also made use of various stainless steel pins and cramp anchors that supplemented the stone shear keys and, where necessary, allowed for tying different stone pieces together, such as at the interior corbel, to prevent overturning. The exercise of 3D modeling all of the stone pieces together allowed us to prepare a fully integrated and rationalized design that also helped with water control. In addition to typical sealants and providing a vented cavity, the joints were all designed in such a way that they lapped in order to shed water as much as possible without allowing moisture into the cavity space. Therefore, while this mausoleum is an example of stone as structure on a fairly small scale, some of the information and strategies could be applied to much larger structures, particularly in how 3D modeling allowed us to prepare an integrated design for all of the stone elements. Here are now a couple of photos of the completed mausoleum. So this is the front view, and following you can also see the side elevation. Now the second case study that I'll present involves a rather different scale and function of stone as structure. The Belmont University Performing Arts Center is located in Nashville, Tennessee, and the entire perimeter is clad with Indiana limestone panels, which are on a steel structure that also incorporates CMU and steel stud infill walls. For this project, stone is used as structure in the form of load-bearing columns, which take weight from the steel structure above. There are 3 sizes of columns on the project: 9-foot tall, 25-foot tall, and 45-foot tall, weighing up to 104,000 pounds for the largest size columns. The columns were used to support the north and south porticos, the tower balconies, and the main entry portico respectively. There are 9 load-bearing small columns, 4 medium columns, and 4 large columns on this building. The columns were tasked with transferring vertical load only, with components of dead load, live load, and wind load. And the design loads ranged from 23,000 pounds for the smallest columns to 146,000 pounds for the largest columns. The structural challenge here, however, was not the applied weight, but the anticipated movement of the steel frame, which was up to 1.65 inches, and in some cases was mainly due to thermal expansion. The problem with that movement is that depending on the type of assembly used, our calculations showed that that amount of deflection could cause cracks at either the stone or the joints. And this was due to a combination of the stiffness of the columns, but also the relatively low flexural strength of the limestone. So the columns would crack before they would deflect. Therefore, our task was to figure out how to alleviate the stresses caused by the building deflection. The solution that we settled on in this case was to use a system of neoprene pads that could elastically deform laterally and absorb the building movement without transferring large lateral forces down to the stone. This slide coming up shows a detail of how the bearing was provided with the neoprene pad connecting the steel structure to the stone. And you can identify another consideration that needs to be made when integrating structural systems, that being the requirement of providing adequate bearing for the steel structure on the stone, because especially with softer stones such as limestone, a steel member that bears on a fairly small point could easily crush the stone if it's not properly engineered so as to adequately distribute that force. In conclusion, despite the large loads that pass through these columns, they were all properly proportioned to avoid buckling. The challenge was actually in connecting the steel system to the stone columns so as to ensure compatibility. The project needed to use a fairly complicated detail, which could have been avoided if the lateral deflections had been reduced. This is why it's important to consider how structural stone will interact with other structural elements from the beginning of the design, so that the benefits of stone can be fully realized. Now I'll pass the screen back to Karl for the third case study.
Great, thank you, Matthew. So I'm Karl Doucas. I'm here to talk to you about the house in the ravine, but more specifically, the special feature stair we executed with an amazing team. The title Stairmaster refers to both the home owner, who revealed to me during a tour of the residence that despite his prosthetic leg, he enjoyed using the 4 staircases in his home, which I thought was awesome. And it also refers to Steve Webb from Webb Yates, whose firm has truly defined some new standards for what a stair can and should be. So we worked closely with his team in delivering this project. This was a historic property and house amidst an urban ravine in Toronto. Peter Clues was the architect responsible for a major renovation to the property that included substantial use of natural stone, and our project, a feature stair extending from the lowest level up to the main kitchen and pool terrace level. There were 3 main expectations for the project. Our client required a turnkey solution for the stair, so we did something we had never done before. We proposed a service inclusive of engineering, material sourcing, fabrication, and installation. And this was a critical decision that we believe streamlined the coordination and closely controlled the technical execution. We had to use G684 basalt to match the extensive interior floor finishes, and we did not have a lot of experience with this material, so some unknown factors in terms of material suitability were top of mind. And our client expected a cantilevered tread design that would extend out from an existing rubble stone wall, but they also wanted it to be simple and economical. Sure enough, after studying the project, we proposed and were accepted to proceed with the eventual solution, a solid tread post-tension stair design. And we were happy that it went that route. So here you can see the lush ravine setting and the exterior wall, which is parallel to the stone stair located on the interior space and opposite the wall. The design of the stair was characterized by the following features. There were 19 total treads. It had a fairly shallow slope of 3 to 5, a major engineering factor with only 6 1/4 riser height. It was only clear of the adjacent wall by 2 inches, but this really alleviated the need to disrupt the historic rubble construction, saving the builder a potential can of worms. So any clearance was acceptable. There was also a mezzanine column that limited our flexibility. The stair had a zigzag profile seen here in elevation. And finally, the integrated structure included an existing steel crossbeam at the top and a concrete slab and new pad at its base that we used for support. So material sourcing. From the outset, sourcing was a challenge. The G684 basalt was a Chinese government controlled material and supply was low from various quarries we contacted. We were lucky to find the material we needed after multiple sources fell through, but it was critical to understand what we had found. We did our own ASTM testing of samples prior to purchasing the full quantity. C97, C170, and C880 tests were done by the NSI lab in Ohio. The critical test driving the stair design was compressive strength. Preliminary design determined that minimum value required was 113 MPa, with average results coming in at 188 for both wet and dry conditions. Density or bulk specific gravity, ASTM C170 was another key confirmation, which would feed the load criteria, and tests indicated 187 pounds per cubic foot for this. Absorption C97 was also done, but less impactful for our interior application. All tests performed well with very small variances, which confirmed the consistency that we wanted. A threaded rod pullout test was also performed for assessing guardrail design. So central input to our analysis was the stair geometry, together with the stone test data, which set our modeling drivers. The stair design, having a long and shallow slope, induced a higher bending moment with increased compressive stresses between the treads. So this would require a heavier force specification for tensioning the steel cables during installation. The general concept was to nest each successive tread to the next by way of a shear key. To create this monolithic beam action, we used continuous post-tension steel cables. In this case, 3 half-inch diameter, 7-wire, low relaxation strands with ASTM A416 grade. Webb Yates took the lead with modeling and stress analysis, and it was an iterative process to achieve optimization. It was tricky to balance the design considerations and the required performance. We did tweak the overlap of the treads a bit to ensure continuity of the strand and shear key geometry, but we're setting a high bar for our fabricators with respect to tooling detail of the treads. Procedures for material prep and installation instructions were just as important as the engineering design, all executed by the Webb Yates team. We at Picco engineered the new pad foundation and the resistance plates at the top and bottom of the stair. We also reviewed and certified all mutual calculations and vetted the required construction materials. Shop drawings were developed for installation and fabrication drawings for each required component, including the stone and anchor plates. Hoist beam and scaffold drawings were prepared as well. Tight tolerances and little room for error demanded super clarity and quality through our documentation. Fabrication was done in Fujian, China, with traditional low-tech equipment and hand methods primarily. Shop progress was monitored through virtual reviews and inspections with on-premises QC by Picco representatives prior to shipping. So in preparation for the install, a temporary wood crib support stair was built using laminated wood members. Our friends at Precision Stone masterfully installed the stone. Each tread weighed roughly 250 kilograms or 550 pounds. A simple raised hoist beam was used to guide each tread into place. Precise and sequential steps were followed meticulously to ensure the cable hole alignment and the 3mm joint requirements. You can see the robust steel base plate design here, connected to the foundation. And tension cables were fed through each tread as installation progressed. And finally, each strand was hydraulically and simultaneously pulled with 10 kilonewton increments up to a maximum of 120 kilonewtons. And that was our final target design tension, at which point each cable was locked in. So if we did everything right in design, fabrication, and install, the last step was a formality. We removed all of the temporary support and the stone was floating for the first time. So that was really amazing to see. We followed a load test sequence to confirm our design and desired performance. 3 deflection gauges were placed on the underside of the stair surfaces, including the beam above. Sequential loading and deloading cycles were iterated, in this case with CMU blocks to record the stair reactions. And our observations confirm that at our greatest CMU load of 3.15 kPa, or just over 3,500 pounds, the stair only deflected a maximum of 0.673 millimeters at the midspan and a tiny 0.051 millimeters at the top beam support. So this was amazing to witness and a validation of all the hard work. And this was the final finished project. Picture 3, the most revealing for me. I actually held my breath the first time I stood underneath to take that picture, but I'm no longer anxious about doing that. So that's great. And the side profile here with perfect replication to the original design. So, thank you to the great project team on this project, the Architects Alliance, Clemenson Builders, Webb Yates Engineers, Precision Stone, and Gonmar Stone. So if you want to learn more about this project, check out our time-lapse video for the full stair installation. I'll make sure all of you get that link to that video. And that concludes our case study portion of our webinar. At this time, I'm excited to introduce Mike Picco, President of Picco Engineering, to lead us into some presentations and our roundtable Q&A segment.
Thank you, Karl and Matthew. I think we can all see there's some great use of natural stone when you get creative and think outside the box a little bit. Those were fantastic examples, and we'll see some more as we move along. Just before I pass it on to our guest speakers, as the Vice President of the Natural Stone Institute, I'd like to share some of the initiatives that the Natural Stone Institute is doing to promote natural stone and sustainability. We all know that sustainability is at the forefront of, oh, I'm having a little difficulty with the mouse here, bear with me. Yeah, sustainability is at the forefront of most projects today. And in light of this, the stone industry has really recognized that we're playing a little bit of catch up with this, as far as getting the message out there of really how sustainable natural stone is. So we're trying to catch up on telling a better story. I know that Steve and Bryan will be speaking a little more in depth on these topics, but the NSI has been working very hard on the subject as well. A few years back, the Natural Stone Council was formed, and there we go. It was a collaboration of trade associations getting together really to join forces to help promote natural stone as an industry. And they touched on everything from commercial, residential, government, institutional, and educational applications of natural stone, which we have great examples of, both interior and exterior, and also in the landscaping trend. And really to increase the understanding with the design and building community on the benefits of using natural stone, especially when we're talking about sustainability and looking at that. So during the course of the several years that they've been working together, they worked very hard to develop a natural stone sustainability standard, which has been accepted by ANSI and recognized as a standard throughout the world. And it's the Sustainable Production of Natural Dimension Stone. So we're working very hard to get the industry as a whole and encourage compliance by all producers and fabricators in the industry. There's 4 different levels. It's based on a point system, very stringent, a lot of requirements that quarriers and producers have to follow. And you can qualify as a bronze, silver, gold, or platinum, depending on the level of meeting the requirements. And if we look at some of the requirements, the goals of the standard were to really establish a set of well-defined environmental, ecological, social responsibility, and human health metrics to measure from. Educate key members of the design and building community, and also to introduce these benefits to many of the green building programs, and many of them have accepted this standard as well. It's also a method for improving the baseline environmental performance of stone, and it really covers everything right from the initial extraction of the stone right to the final fabrication. When we look at the ecological responsibility, really promotes responsible quarrying techniques. We know that there's an abundant supply of stone out there. A big focus on using as much of the extracted material as possible is a big focus, and trying to minimize any of the waste of the raw material. Quarry reclamation plan is a huge part of it. What's going to happen at the end of the life of the quarry? What's the land use going to be? And also respecting the habitat during the quarrying and lifetime of the quarry, and also after. So these are some of the ecological focuses. From an environmentally responsible, we know it's a natural material, does not off-gas VOCs. Life cycle cost is very low. It's obviously recyclable. It's coming out of the earth. It's a natural material. Very low embodied energy. It's chemical free. And water reclamation is also a big part of the program, because water is a big component in the fabrication. So reusing, recycling water is a big focus as well. The other thing that it touched on is the social responsibility and the human aspects, finding companies that are giving back to their communities, really focusing on health and benefits of the employees, adaptive reuse, and safety throughout the entire process. The Natural Stone Institute also has a fantastic dimension stone design manual. It's available download for free on their website, and it's a great resource. I strongly encourage people to download it. Touches on the physical characteristics of different types of stones, specifying installation methods, both interior, exterior, and maintenance as well. So it's a fantastic resource to have in your library. I strongly recommend it. One of the other big initiatives right now is education, and they've got several different ways to get CEUs on the website. There's webinars that they're working on. There's online courses that have been developed that you can take on your own time. So again, I really encourage you to go on the website. There's the educational program on there, and it gives you a program of all the available courses and educational tools that are available for you there. So without further ado, I'd like to pass the presentation on to Steve Webb. Take this opportunity to thank both Bryan and Steve for joining us today. And it's great to have leaders in the industry to join us to collaborate on this this great topic that I think is really we're really gonna see some traction on it in the future. So without further ado, Steve, thank you very much.
Great, thanks very much for having me as well. Yeah, so we're Webb Yates. We're about 65 people. We do structural engineering, mechanical and electrical, building services engineering. We have a few architects. I think something like 5%, or maybe only 5% of our turnover is associated with stone, but I think stone is something that we're very particularly interested in. We work on quite a wide range of jobs. So we set up our practice doing little residential extension, loft conversions and things like that back in the day, 15 years ago. And we still do those sorts of jobs. We do bigger jobs as infrastructure, airports, big job there at Heathrow Airport. So we work across a lot of stages, and we deal with kind of unusual problems, unusual material problems. We work with inflatables and cork and all kinds of different things, which is, I guess, how we ended up working with stone. So yeah, stone is a great material. There's a lot of it. I think that actually all of the buildings in the world, if you assigned everybody in the world 30 square meters of 200mm slab, that would be the equivalent of 2 Ben Nevises. And nobody knows what Ben Nevis is. It's the biggest mountain in the UK, which is a relatively tiny mountain by most people's standards. There's a lot of stone in the ground, and the volume used in edification is very small. Usually, we dig up stone. We would dig up a piece of granite like this at 200 newtons. Maybe we dig up some limestone. We crush it using a lot of energy. We get a lot of gas, and we burn the limestone with clay to make cement. Cement works. We send that all off to a state-of-the-art batching plant. Mix a lot of water into it, mix a lot of sand into it. Actually, sand is limited, which is quite surprising. We form it up, we reinforce it, we put formwork around it. I have a very slow connection here. These slides aren't ticking over as fast as they're supposed to. And at the very end of that, we end up with a piece of concrete with a strength of about 40 newtons. So it occurs to me that it might be better to use the stone in its raw state than to go through all of those industrial processes and end up with something which is actually inferior to what you started with. Yeah, so this is a relative, so the font size on this slide is the relative strength of stone divided by its carbon footprint, and the relative strength of concrete divided by its carbon footprint. So stone is much stronger than concrete, requires far less carbon in its production. We are interested in the swings and roundabouts of using different materials. So this slide is looking at a beam that spans 2 meters supporting a 1-ton car. So kind of 2 meter span beam, fairly small, typical application. Looking at different sections that you can use to perform that duties. So on the top row, we're looking at softwoods, steel, post-tension stone. On the bottom row, so there's equivalent sizes. They're all strong enough, 2.1 millimeters of steel. It's very effective. The middle row are the equivalent stiffnesses. The bottom row are the carbon footprints per meter run for those beams in those different materials. So you can see if you use a steel beam, even though the steel beam is incredibly small and incredibly slender, it's actually using 22 kilograms of CO2 per meter, while the stone one, or the post-tension stone one, is only 1.5. And timber is, timber is a good environmental solution, but actually that also requires quite a lot of energy in its production. It isn't as strong as stone, so you get kind of relatively higher carbon footprint for the initial use of timber. So counterintuitively, well, not counterintuitively, stone is a really good material from a sustainability perspective. Quite often, I mean, the stones we use in the UK, I guess the stones that you're using over there in Canada, granites and limestones, much stronger in compression, much stronger in tension than concrete, which is the really useful thing. So we have to put far less reinforcement into stone because of its tensile strength and because it has a reliable tensile strength, whereas concrete doesn't. The issue with stone, or the thing that I think probably scares most practitioners from using stone is the fact that it's a naturally occurring material and it's not homogenized in the way that steel or concrete is. So you have a slight unpredictability in the material properties. So we have to do quite a lot of testing. So whenever we're using stone for different applications like staircases and stuff, we do a lot of tests to establish how strong it is. We came into stone design by designing staircases. So we were designing traditional stone cantilever staircases like this. We were doing other more refined versions. So this is a modern version where we're cutting out low stress stone. In this case, the stone is completely unreinforced and it's using a kind of torsional reciprocation for its support. We did a lot of versions of these kind of stairs. Working with stone masonry company, they were limited to selling staircases where the flight sits adjacent to a wall. So as long as the stair is next to a wall, anyone can sell this kind of staircase, but actually many staircases aren't in that situation. And so they were really interested in developing a system for free spanning stone stairs. So we started looking at reinforcing the stone, how we could reinforce the stone. We're not in any way near to the people who invented reinforced stone. There are lots of examples of it. Companies in Germany and Renzo Piano and Hopkins here in the UK. We produced this early prototype. So these are effectively, this is like post-tensioning together 4 50mm paving slabs to span 3.2 meters. There are 2 8mm cables on a parabolic trajectory. Post-tensioning means that all of the stone is in compression. Normally with reinforced concrete, it's not in compression. Well, not all of it's in compression. And that with stone, you're not getting, because of the higher strength, the compression in the stone isn't anywhere near the ultimate strength of the material. So you get far less creep and shortening. So concrete quite often sags because of the long-term creep effects in concrete, whereas actually stone doesn't really suffer from that problem so much. So we ended up, in this case, making a 50mm stone plank span 3.2 meters with 2 8mm cables. I think this is very, very effective compared to concrete as a material. We developed that through various projects. And I think we develop ideas in our practice and we tried to do small jumps at a time. So we kind of went from a small straight flight to a slightly curved flight to a bigger flight. This one was a 270-degree helical flight. This treads a solid stone. There are 2 12mm cables with 12 tons of pre-stress in each cable. We did some prototyping, discovered that the order of tensioning the stone has quite an impact on breaking it. Learned a lot of lessons during this process. So this is a stone masonry company, Pierre and Paul, doing a 75% scale test. We solved those problems, resolved in our analysis, and finally got it working. And we developed quite a lot of analytical methodologies for how we can how we can analyze these things, how we analyze the joints in the stone, how we analyze the behavior of the stone itself. So this staircase is in Formby, just outside Liverpool in the UK. It's 1.4 meters wide, it's 270 degrees. I mean, we spent a long time calculating this, and when we saw the photos of it, I was really shocked, I have to say, kind of wanting to recheck all of the numbers. It's you know, it's a really arrestingly surprising structural thing. We're also interested in what you can do without reinforcing the stone. So, I mean, we have surrounded by 1,000-year-old Gothic cathedrals, tiny vaults, fan vaults, all kinds of things spanning without any reinforcement, big spans, columns, all kinds of stuff in the kind of in the Gothic era, France, UK, all over Europe. Amazing, without reinforcement, without mathematics, and without analytical. It's quite surprising. This was a small staircase, was going to be a steel stair clad in marble. It was then going to be a post-tension stair. We decided to try and make it work unreinforced. So these are our polystyrene model. We thought if we can make it stand up in polystyrene, then we can make it stand up in stone. This would stand up for about 3 seconds until somebody breathed on it, and then it would fall down again. But we basically worked out the static principles for how the treads were going to interlock. So we've got an arch on one side of the stair, a torsional cantilever stair on the other side of the arch, and then an interlock between those landing pieces so that they can't fall out. This is a silver travertine, which is quite expensive. These are the things being erected. I should say all of these stairs, there are kind of cheesy handrails being put on these afterwards. We send the photographer out there before the handrails go on because the kind of stone on its own is more interesting. But yeah, so that stair, no steel, no ties, no clips, no stainless steel dowels, just stone all the way up, which I think is kind of interesting. I should say this stair cost £750,000 quid, so quite an investment on part of the client. We had to, the stair weighed 16 tons and it was on the 4th floor of a 1920s building on a 6-inch slab, so we needed to support it. There was a solution to put a whole series of beams underneath it that would have resulted in a step at the bottom of the stairs. We tried to find a solution that we could hide in a 75mm screed. So this is a 50mm steel waffle plate built with an upward curve, so pre-stressed upwards, so that when the weight of the stairs is applied to it, it goes completely flat, and then at that point it makes contact with the slab underneath. So we made this curved waffle, then we jacked it flat, then we built the stair, then we unjacked it. We were absolutely terrified that we got it wrong and this thing was going to ping the staircase back off again, but by some miracle we got the numbers right. This is by hard work and expertise we got the numbers right, not by some miracle, I should say. This is a sculpture by Anthony Gormley. Anthony Gormley wanted this thing to last for 200 years and he wanted it to be demountable and reassemblable, which sounds so straightforward enough at the beginning, but then you realize actually then you can't see any bolts, can't leave any visible bolts, you can't grout it together because you can't take it apart again, and suddenly that becomes a massive problem. We thought, again, really interesting to try and make it work, try and make it balance without anything else. So this is his body. You can see his head is the big block on the right hand side resting on his arm. You can see his leg lying on the floor, his ankle and foot, whatever. It's a kind of self-referential thing. So again, we experimented with the polystyrene block model. If we can make it balance with the polystyrene, then it'll balance with the stone. Did a lot of analysis. We had to very slightly change some of the positions of the blocks. So all of these blocks sit, they have to be assembled in a certain order. They have tenons that project into sockets in the back of the stone. They sit on Lego nipples. The Lego nipples are arranged in such a way that the stones lean against each other. If you put one piece of stone flat on top of another piece of stone, you don't quite know where it's resting, and it's going to rock because you'll never get it completely flat. So having 3 kind of Lego nipples making really enforces on the stone where it's going to sit. So all of this interlocked, it can only be built in one order, it can only be disassembled in one order. So the whole thing was built without any artificial, well, artificials are all artificial fixings. So we really want to start reintroducing stone back into ordinary buildings rather than just doing luxury staircases and novelty jobs. So this is kind of early version of that. This is a concrete frame building. This is our BIM model, so you can see the core kind of shadowed inside there. There are no concrete columns. Concrete frame supported entirely on an external stone frame. That's the concrete frame being built. It's kind of not very expedient to have one contractor building something and then another contractor building the supports. You want to give one guy the site and give another guy the site afterwards. So in this case, the concrete frame was built, left on props. Stone frame was put up afterwards and erected. Building was depropped. The aspect ratio of this presentation is a bit squashed. I think that building's slightly taller and less wide in reality. But yeah, those stones, those are the finishes in the stone that came from the quarry. So this is a stone masonry company job. The stones were drilled, feather wedged and split. So you get the split face, you get the wedged face, and then you get the cut face. So there are 3 different finishes, pretty much arranged randomly around the facade. The building's entirely supported on that stone. The stones get smaller as they get closer to the top, smaller at the edges. This building got a pretty hot reception from the local community. There was a bit of a planning scandal. People were kind of opposed to it, but actually we found when people realized the stone was load bearing, that there's actually more content, there's kind of honesty in the facade. People want to it quite a lot. And this is a kind of future development thing we've been doing. If you get a Mickey Mouse tile puzzle where you slide the tiles around to make Mickey Mouse's face or whatever, kid's toy, plastic tile puzzle, there are no rails in that tile puzzle. You can turn the thing upside down, the tiles don't fall out, and the hole can be anywhere. We're thinking this is a really interesting principle. I mean, we can do that with stone. So we were invited to submit something for the V&A in London as an engineering season. So this is 3 meter by 3 meter slab made out of 40 millimeter Portuguese Mirabel limestone. It's supported on the 4 edges. It's not supported in the middle. The tiles are clipped together so that they can't vertically translate. There's no reinforcement or ties or steel work or anything underneath there. So we can span. We built it in about an hour and a half. Very thin pieces of stone, span 3 meters. No reinforcement, no concrete slab, nothing. So I think this is a great idea to kind of roll out, solve other problems. Perhaps a solution for a kind of future building system. So we're thinking in lieu of building a concrete frame, concrete wagon or whatever, you bring in columns, post-tension stone columns, post-tension stone beams, and you make big stone floor plates with thin pieces of stone slab interlocking in this way. So you can have a largely reinforcement-free stone frame, very quick to erect, demountable, reusable, upcyclable, and very low carbon. So I think applications, not necessarily this, but applications like this for stone to start to supplant higher energy materials like steel and concrete, I think is what's really interesting for us, if we can make them affordable. I think that's the end of my talk on the title changes.
There's one more.
There one more? They're changing very slowly. Oh yeah, there's me effortlessly supporting my weight.
Great. So 1 second here. Thank you. Okay, so thank you, Steve. I know, I mean, that was a great presentation, education there on some of what you're doing in stone and really pushing the envelope of what is possible. So thank you for that. And now I'd like to invite Bryan Thorburn, Director of Business Development for Europe and Middle East, to say a few words.
Hi, everybody. Many thanks to the team at Picco Engineering, Karl, Mike, Matthew, and to Steve Webb as well, who I've gotten to know over the last year or so. It was a presentation like that Steve did for me, I think, over a lunch in Paris, which made my mind start turning in wonderful ways. And that's because what we do is the very source of the material in the quarry itself. So been asked to speak to you a little bit about the actual source, the quarry, and what we do. So do I have control?
There you go.
Maybe. There we go. Ooh. So a quick story about Polycor. We are primarily a quarry company. We own 50 quarries, own and operate 50 quarries in North America and in Europe, in France. We also have 17 manufacturing plants, a big diversity of different products that we produce, whether it's countertops for a kitchen, cladding for a building, paving in your local park, or curbstones, which you drive past every day. We have 17 manufacturing plants, about 1,100 employees. What we specialize in is dimensional stone, building stone. So this new concept, or I shouldn't say new concept, ancient concept, I guess, that is new again, of building with stone is a great interest for us. A few of the things that we've been very lucky to be a part of with our stone, the Empire State Building with Indiana limestone, projects right across North America, Canada, Europe, and the Middle East as well. Again, we specialize in dimensional building stone, not so much that exotic, expensive stone that's imported for the bar, your local bar worktop, for example, but stone that's specialized in building. And historically, that's what stone was used for. I mean, there was only stone back in the day. You had stone and wood before concrete and steel became part of the norm. Quarries were quarried quite differently back then. Block sizes were smaller. Block sizes were taken from the quarry that were more corresponding to the actual blocks that were probably going to be used on the building itself. In some ways more efficient, some ways less efficient with machinery and modern techniques that we have now today. But this was the way quarrying was historically done. Certainly much of what built America, North America, and Europe after the war as well, and before. But with time, with the modern era, shall we say, the concrete, cement, steel era became those chosen materials for, first of all, they were fast, they were cheap, they were predictable, and stone took a more and more aesthetic orientation. People were looking to, in fact, the stone got thinner and thinner and thinner to the point where we're almost wallpapering concrete and steel buildings now with a small layer of stone. If it's cladding, if it's paving, and maybe in the landscape world, we see a little bit more stone being used. We see thicker material because obviously you need a compressive strength. You're going to have people walk on it and drive on it, and they still, to this day, haven't come up with too many man-made materials that can achieve what stone can do and hold up so well, be so durable, and take it for the long run. But what most of the stone industry is geared toward is aesthetic, thin slabs, thin tiles, maybe thin cladding for building. We see rain screen curtain walls that are getting thinner and thinner. So this is where the industry is geared towards, and then very, very large slabs as well. So you see 2, 3, maybe 5 centimeter, a little bit more when it's landscape. But again, it's geared towards very thin material, and then it's all about the aesthetics. We're using it pretty much as that final aesthetic finish. Therefore, a lot of stone can be either not used or wasted because it's just not considered beautiful enough to put on the building. This concept of building now with stone as the structure itself, we take the focus off the aesthetic and we put the focus back on what stone is good at, which is being heavy and strong and tough. When we just look at the aesthetics, here's an example of a stone. It's a beautiful stone. It's a limestone we have from Oklahoma. You can have some architects who will say, yes, let's use it all. We love the stone. We love the range of it. But if, I don't know if the slide is going to come up, but you may have a design intent where you want it extremely uniform. We cut out half of the material. It's either not used, or maybe if we're lucky, we can use it on another project. But again, it's all about the fashion, the aesthetic, the final look of the material that the entire industry really is geared towards. And we can also look at stone. Well, I just put up a pink granite slab, which is a little less in fashion now. But there's some amazing stones structurally out there, granite especially, which maybe have fallen out of favor. Maybe there were very active, productive quarries, and these stones we can start looking at these again, less for their aesthetic and not for what's stuck on the outside of the building, but what's holding up the building itself. As we start seeing this trend, which we've seen more and more in Europe, especially, Steve helped introduce it, but also a number of architects here in France and other parts of Europe as well, who are looking at stone as a structural element again, have helped us kind of rethink and maybe even go back, I guess, as some of the masons and installers have done, is look at how can we start looking at quarrying and making it more affordable. Steve was saying, if it gets more and more affordable, then we can see more and more of the use. We know we're saving on the carbon side, but what about the financial side? So this is where we start rethinking quarries and start adapting them as maybe as they once were, and start looking at optimizing the format so we actually cut the blocks that we need, not necessarily to make a giant slab that's going to go as a countertop somewhere, but start pulling blocks in a large quantity in the sense that we can build with it now. That's a viable size and formats that are optimized for the quarry itself and also for the final product. So there's the least amount of manipulation and cutting to be done. It's going to save carbon, it's going to save time, it's going to save money. Also, we need to start thinking about how everything's being fabricated as well once it comes from the quarry. We do have a number of manufacturing plants, and each manufacturing is going to be adapted specifically for the material itself or for the final product of the material. And this, I mean, the industry right now, again, geared to very thin material, is going to be much different in the case of structural stone. We're going to start getting thicker, whether it's 10, 15 centimeter thick, or up to very large blocks, with a few examples of which I'll show you as we go. Again, what we want to do is optimize the production. Any quarry, if it's going to be healthy, we want to use as much material from that quarry as possible, however it's going to be used, and whatever doesn't make it through the manufacturing of maybe large pieces, we can find more uses for down the road. The other factor that we have to think about in the factories itself is how we're actually going to start introducing some kind of protocol for testing. Steve mentioned that one reason that some people maybe are hesitant to use stone is the unpredictability of it. The tests exist. It's a question of how can we start implementing that, not just a test that's being done every 10 years, but maybe something that we can do within our factories. All of that has to be done, and in fact, it's already there. There are already manufacturing processes that are capable or adapted for it. I think of maybe a curbing situation where we produce granite curbing right next to the quarry. Transportation is very minimal, waste is very minimal. We're able to optimize the most amount of material. So it's out there. It's the question of re-gearing towards creating a sustainable way of building stone that's structural stone. Getting back to the testing, these are the things that we have to look at. These are like the things that we're going to owe to the architect and design and engineering community, because we need to have some kind of accountability and also some kind of assurance that we have a plan to present the material in the best way. There's two different kinds of testings we can look at, and we're looking at as well as we get more into producing material for structural projects. One of them is destructive testing. These are the traditional tests that already exist, whether they're from compression, flexural, density, and porosity. These are all important tests where a lot of quarries we found people come to us and say, well, we tried to use this other material, but the best we could get for test data was from 1984 or 2002, and it's all outdated testing. So part of what we have to do from the industry is to be able to provide up-to-date testing, and to the point where we could also implement, in the case of, for example, if we were going to produce the flooring slabs that Steve is looking at, those interlocked flooring slabs, which are maybe 10 or 15 centimeters thick, in-house systematic testing where we test every certain number of blocks, whether it's spot check or depending on the zone where the quarry comes from. We actually do our own in-house testing, as well as some verified third-party testing as well. On the non-destructive side, there's a couple of relatively simple things that we're looking at that we can do as well. One of them is the visual classification of grading, which we see in the timber industry already. They have a system, it's standardized, and people have come to accept it because it's very, very effective of what you can see with your eyes on construction material. is very good. So a visual classifications grading, but also from the concrete industry, we're investigating some ultrasound pulse velocity, which essentially will tell you the density, the E modulus of the material. Not applicable in all the different, we can't shoot it right through the quarry, but what it can do is give a very good sense of a non-destructive test, which can show us the consistency of a material, not that difficult to introduce very systematic testing. So what we owe to those designers and architects, engineers that are looking to start building with stone, as structural again, is to have something we can bring to the table and say, here's what it is, here's how often we test it, and here's how we grade it. The other thing we owe is to start introducing this idea of standard formats. When you introduce stone, here's a block, do whatever you want with it, that's a great thing. But it's also a great thing to say, here's some basic building blocks that are affordable, that are produced, that are tested, that there's some quality assurance, and this you can start building, and it makes it a lot easier for BIM implementation as well when you've got something standard somewhere to start with anyway. Part of the keeping those costs down. Something else we owe are EPDs. Mike talked about the ANSI 373 certification. This is something that is important. It's like we've intuitively known in the stone business that we're green. It's a very simple process. We cut the stone, we put a little bit of diesel in the truck to move it from one place to the other. We then cut it and it's done. We're not cooking it. There's no added energy. The embodied carbon in stone is inherently very low. What we haven't been great at until now is some kind of third-party certification where we can stand up and tell everyone that it's sustainable and clear. And that's why having certified EPDs and the ANSI ANSI 373 certification is super important. Ethical sourcing as well to include the sustainable side, but also the social impact as well. We need to have that for stone, as they do in the timber industry with any other material there is. And the last thing is the kind of maybe the most heartbreaking part is after how many thousands of years or more of building with stone, a lot of that knowledge is still with a number of great people, but it's certainly fallen pretty far behind in terms of the basic knowledge of building with stone. And so I think what we owe is some kind of place to start with for where to begin, a kind of basic handbook of masonry that becomes standard. It's not something we have now, but it's something we would like to see put together. I think we're going to need that for it to take off. A few different projects we've been lucky to work on in the last couple of years. Load bearing, maybe less cutting edge than some of the things Steve has shown us, but equally strong and durable for the ages. This is the British Memorial in Normandy that is just going in right now. It's hard to believe, but there was no actual British memorial there until now, which is being done in Massangy French limestone that we have. There's about 180 of these load-bearing columns. They're about 4 or 5 meters high. There's also another a very large court wall. It's about 22,000 names engraved into these columns. That's looking at the much more traditional side of the load-bearing masonry. But some other projects that we're seeing done here in France, for example, some of the images there you see from Perrodin Architecture, which are some wineries, as you have in France, of course, built with stone, solid structural stone, as you see several examples. And here it comes. Another project done in France as well, which is part of our building, the building center exhibition. Load-bearing stone, not necessarily doesn't have to be a 1,200-year-old cathedral. We can see some modern implications as well. This material, this building built entirely of stone and some wood structure as well. Another example of a winery there in France. And we're frozen. Steve showed you the images of Clerkenwell in London, done by Amin Taha and group work. This is possibly taking that to the extreme. We did a case study to see how feasible it would be to put together a 30-story building using this concept of the exoskeleton stone, load-bearing stone for the entire structure. we discovered, or I shouldn't say we discovered, because they did the study with the 5-6-story version of Clerkenwell, where using stone in that context as the structural material saved 92% of the carbon had they done it in concrete or steel. The embodied energy savings is spectacular when you compare it in that sense. And this was a great study to do a 30-story version, similar carbon savings as well. And oh, that's right. And the amazing thing, and part of the energy savings, but also the cost savings, is the fact that the stone itself is the finish. We don't need to start engineering the sandwich of every layer and waterproofing and all that is in between. The stone itself is the finish. This can help in the cost, but also the aesthetics of the building. And then another project in development. This is a 20-story mixed-use residential building in Switzerland, designed by Perronin Architecture, 20 stories high, also in load-bearing stone, a little more on the traditional side. And that's it, just to show you a few of the things happening here in Europe.
Great. Well, thank you, Mike, Steve, and Brian. Amazing to hear your presentation speak about the sustainability of stone and the opportunities, examples through the great work that you're all doing. For all of you still on the call, we are running a little bit late, but we do want to get into kind of the roundtable portion and ask some real pertinent questions. And so here's the first one. Why is now the right time for structural stone design disruption or rediscovery? And Steve, why don't you tackle that one for us?
Yeah, I think, I think that the broad adoption of steel and concrete as a solution in the 1930s for building really was based on the idea that we were going to have limitless energy, that they were seeing endless oil reserves, nuclear power, all kinds of stuff. There'll be no limitation on energy. Clearly, there is now a real limitation on energy and a real drive for sustainability. And so using the materials that are right under the ground as part of the solution for that, I think means that, I think it's wrong that stone was left behind as a building material anyway, but I think that the sustainability issue really puts it back on the agenda.
Right, and you've made some great points related to sustainability and how to really view stone and the carbon footprint and the small carbon footprint for sure. So thanks, Steve. Brian, this one's for you. How does sustainability factor when the use of stone at structural dimensions often means using significantly more stone than traditional rain screen or thin panel facade applications?
I think the black bars that Steve showed in the slide there, where you see the carbon footprint versus tensile strength of the material, I think shows it very well. The more stone that goes into the building means the less concrete and steel that goes into the building. So you have just there your far less embodied carbon in the building itself, actually in the actual material that's going in. The other factor there is the longevity of the building. I mean, their buildings are now set to survive 50 years in many parts of the year, in many parts of the world. There are buildings now that are 2,000–3,000 years old, built in stone. If you look at maybe that's the extreme, of course. We're not building for 3,000 years, but we certainly see the durability and the resilience. Building resilience is very important right now. This idea of fire resistance and flood resistance. So all of that factor goes in to show that it ticks all the boxes basically in terms of the longevity and the lack of the very, very low carbon use in it. Then also on the other side, as you have more stone and less we've kind of built these super airtight insulated greenhouses now that we need to cool. We need a lot of energy for the air conditioning. All of those arguments that the concrete industry talks about in terms of thermal mass of the operational energy of a building is super, super important when it comes to the stone itself. We just think about those beautiful Mediterranean homes that stay cool even on a hot day. It's because of that thermal mass. It breaks that curve of having to add more energy for the cooling and the air conditioning. So and that's maybe a challenge that we have in terms of the building of this becoming more and more accepted in terms of the norms. But what we do know is that thermal mass of a thick stone wall, for example, is going to help you in terms of cooling. And I guess the reason that we're here and probably talking about this is because it's not getting cooler.
Right.
It's because of rising temperatures. So I would say the two, that you've got the embodied carbon and the operational carbon between both
Great.
of them.
Yep, thank you for that. And for sure, you have all shown that the talent exists to bring this type of technology or this rediscovery of solid stone construction to the market, for sure. So Mike, what are your thoughts on this question? In your view, what are the biggest challenges to using stone as structure in construction, and how do we overcome them?
I think the biggest challenge is really acceptance by the design and construction community. As Steve mentioned, it was the norm back in the day, and then through the 20s and 30s was left aside and kind of ignored as a building material. So I think we need to, it starts first with the architects and designers reflecting back on the successful use of stone as structure, and we've got, as we mentioned, many examples of it throughout the world. And from a technology and an industry perspective, as Bryan mentioned, maybe quarries now and fabricators have to rethink some of their processing, some of their retooling, potentially with some fabrication shops going to more cubic material handling might be a little different for some of them. Some of them may be very easy to adapt, but I think that's another area where there's going to be a little bit of a challenge maybe for some. But I truly believe that, if we do enough research on the benefits of going to natural stone in various uses, I think we'll start seeing more and more acceptance, because there are huge benefits there for sure.
Great, thank you for that. We do have a question asked from one of our attendees, and I'll pose it to all of you. Bridge of knowledge. What are your suggestions to bridge the knowledge gap for architects, engineers, and especially building departments related to stone and structure? Who'd like to jump in on that one?
I'll just mention something quickly on the building front. We do always have challenges with building departments, even putting 2 solid columns at the front portico of a house, demanding that we need a steel column in there. You can't use the stone. And I usually try and defend it by bringing a bunch of pictures of cathedrals in Europe and saying, well, none of these have steel columns, and we're supporting a 10-foot by 10-foot portico, I'm pretty sure. But there's a challenge there for sure, because it's been ignored for so long that there's definitely a gap, and a lot of people are uncomfortable with it. So I see that as definitely a challenge. Maybe you guys can chime in on the architects and education front, maybe.
I think from our side anyway, it's going to be soldiers on the ground of one by one finding those people who are open to it, that are trying it and pushing it, and then to be there to answer the questions and be there with the testing that they're going to need, and to be responsive in that way. For our side, on the quarry side as well, I think we need to implement some kind of new industry-wide handbook of some kind that is something like the Dimensional Stone Guide, but maybe something, I don't know how much structural information is in that. So maybe there's not that much. But the big thing, I think, is to start tapping into the actual artisans that are working with stone all the time. It's still there. It's just become very, very niche. But that knowledge is still there. There are still ancient medieval guilds in Europe and in France of these guys. I'm getting a little bit Da Vinci Code here, but there are actual masonry practices that are still being handed down from apprentices and masons and guilds and the local masons. So it's tapping into that.
Great. Let me jump in. We do have some more questions, and I'm maybe jumping all over the place, but this is a question for Steve. Can you say a bit about the conference, the New Stone Age in London? Is it still going on? I was going to go there, and then COVID happened.
Oh yeah, no, they reopened it. It's open till 28th of August. So yeah, come along. That's great.
Great.
September 14th, I think. I think it's September 14th. Sorry to correct you.
Oh, is it? Oh, they extended it a bit longer. I just want to come back on the previous point and really echo what Bryan was saying about using it in building. We need a code of practice, a design code like the concrete code, like the concrete model code, something which has international acceptance, and we need grading of stone in quarries. Engineers are terrified of designing with stone. They don't know how strong it is, and they don't know how to design with it because they haven't got a code. Very simple. Actually, the amount of work that went into making the concrete model code would be immense. I mean, a lot of testing, a lot of laboratory testing, a lot of different people in different countries agreeing and working on. So I think we're starting to do a little bit of R&D in the UK at UCL, slightly sponsored by Bryan's company and Stone Masonry Company, and I think other people are doing research, but it needs a proper effort at codification. The minute you have a Eurocode or a, what are yours called, ASTM?
ASTM.
Grading code in your hand, then the building control guy, the building department has nothing to argue about because he's got it in a book.
Great points. There's one other question here. How is cost affected in the delivery and marshaling around job site? If that's something, maybe, yeah, Bryan, maybe you can address that.
Stone, I guess the question is directed stone versus another material because there would be more volume, for example.
Right. I guess the space requirements and kind of logistically managing solid materials around job sites and the tight spaces that we all kind of work in from job to job.
Yeah, I guess it certainly depends on where you are and what kind of space challenges. But I think so. Space challenges are difficult anyway. And with modern logistics, I mean, we find that we're usually delivering per schedule. We have project managers who arrange the priority of that. So, I mean, we're doing projects in New York City that don't have room for anything really. So it's just-in-time deliveries. It's deliveries from a yard to the job site. I think the logistics are there already. But in the case of maybe that 30-story building, yeah, we're going to have to come up with a good plan to make sure that the flow of stone is coming, and then there's somewhere to store it, because it is quite a big volume. But again, we're not changing the volume of the building itself. I mean, there's still material that has to go into that building in some way.
Right. Great. So, Mike, go ahead.
Well, so I was going to say, I mean, this idea, the hegemony of concrete, I mean, the stupidity of concrete. If you're an alien and you landed on this planet, you said all these people are sitting 3 feet above an infinity of stone, and they've got mixer trucks, you know, full of mashed up stone to make concrete, you know, the logistics of concrete, the logistics of getting stone out of the ground, turning it into concrete and getting onto a building site are just bonkers compared to getting a block of stone, putting it on a truck, taking it to site. The concrete goes off in the wagon.
Right.
You know, you get the concrete trucks backed up down the street, they have to go and empty it into a skip because it's going to go off, you know, or it goes off before they get it on the building. You've got to pump it up the building, you know, I mean, you've got to vibrate it, you know. This is a complete circus of stupidity to use concrete. And then you have a truck with blocks of stone that don't go off, are immediately set, don't need 28 days of curing. I mean, people are, you know, what are the logistics of stone? You know, the logistics of concrete are just totally unlogical. You know? Sorry, I'm going off on that.
No problem. Great points. I think most we agree with those. Let me just end with
one
last.
Everything you just said.
Go ahead, Bryan.
I just said I agree with every single thing Steve just said.
Perfect. Let me just end
coming from a true stone guy.
Yeah.
I know, but there's something inherently simple and pure about it that anytime I've had this discussion with someone, people, I mean, it's just seems to me to be an extremely clear, logical.
If I said to you, you've got 2 ways of delivering a material. One is you put it on the back of a truck and you take it there. And the other one is the truck has to have a revolving tank on the back of it that has to keep revolving while the truck drives around. You'd be like, oh, yeah, we'll go for option 1. The hell are you talking about option 2? It's just,
there you go.
Great. Well, I mean, thank you all for joining us. I am mindful of the time we have gone over, and but great discussion, great engagement, and some good questions put forth as well. At this point, I'll just turn it over to Mike Picco for some final words.
Yeah, at first I'd like to thank all the attendees. I mean, even though we've gone over, I think we may have lost one. So I think the engagement was great because everyone stayed on. Special thanks to our two guest speakers and colleagues in the industry, Bryan and Steve, for joining us today and sharing your expertise. I think it's really added a lot to the conversation, and also spreading the word of the benefits of stone. I think we're all on the same page of the proponents of it to be used more in the industry. Karl and Matthew, thank you for putting it together. Sarah and Karen are in the background just in case we needed some technical help, so they've been keeping an eye on us. And it's actually worked quite seamlessly with, people all over the world here. So it's a fantastic way of using our technology to get information out there. And I guess one of the enlightening parts of the COVID, although there's not too many, but I think we've also gained a lot of great learnings with things that we're doing like this now. So thank you all, and we look forward to seeing you at our next webinar. We'll be posting. We're planning to do them on a monthly basis and touch on different topics. So thanks to all the attendees, and again, thanks Bryan and Steve for your contribution. Really appreciate it.
Thanks for having us.
Thank you very much for having us.
Great. Thank you all.
Thank you.
Take care.